So let's now take a look at how does this phenomenon appear at high energies, X-rays and gamma rays. And what's shown here is X-ray picture of the moon from Rosat satellite. And you can actually see that there is moon. It's illuminated one side. This is reflecting solar X-rays. So you see Terminator. Ironically, the first X-ray observations in astronomy were done trying to detect moon, and they didn't. But much later with satellite, they took this picture. So the beginning of X-ray astronomy was one rocket flight in 1962, led by Riccardo Giacconi. Here he is. And he got Nobel Prize for this 40 years later. And in that one rocket flight, they discovered first cosmic X-ray sources other than the sun, and also uniform background of X-rays coming from everywhere, which is now called a cosmic X-ray background. And it turns out that that cosmic X-ray background has, a few percent energy of the integrated starlight or the universe, and that's a few percent of the cosmic microwave background. But this was discovered same time, or actually a little before, the cosmic microwave background. And as soon as we understood there are such things as quasars and so on, it was thought that this background must be due to integrated emission of many, many, many active nuclei over the entire universe. And that's in fact the case. But there was an issue with its spectrum. In gamma rays, this is definitely the case. So now if I expand picture of what's the spectrum of the universe over 13 or so orders of magnitude in frequency or wavelength. Well, you have a very narrow Planck function in the radio or microwaves. That's the cosmic microwave background from cosmology. And then you have actually two bumps in optical and far infrared due to the starlight. And then at high energies, you get, again, almost flat, but not really completely flat cosmic X-ray background and gamma ray background. So that bump was what was puzzling people for a long time. This does not look like a spectrum of an active galactic nucleus. This is measurements from many different satellites combined. Instead of that, it actually looks like X-ray spectrum of hot gas, the Bremsstrahlung radiation, just like the hot gas in clusters of galaxies. But we knew that the universe is not filled uniformly with hot X-ray gas, because the well-isolated sources. And so the answer was, in the end, that this is a combination of X-ray emission you see directly from active nuclei, just as I was telling you earlier, and also reflected X-rays, because remember there is that dusty torus, and so X-rays do go through a lot of stuff, but some fraction of them can be reflected off of dust particles, and that has its own spectrum. So if you have proper combination of things, you can add up something over all different redshifts to something that looks like this. So now we think that in fact all of the X-ray background is due to a combination of mostly active nuclei with some star formation thrown in. And the way we know this is people looked at very deep fields. So just like optical astronomers had some deep fields like Hubble deep field and ultra deep field and super duper deep field and whatever, and then added a lot of integration together to see as deep as possible. X-ray astronomers did the same thing, and they did it again in the same fields so that there is an optical counterpart for every X-ray source. That's fine. And they do have a variety of properties. Some are near enough that you can see a host galaxy. Some look star-like. Those are quasars far away. And when you add them all up and extrapolate a little bit to what you cannot see as individual sources, that can pretty much account for both soft and hard X-ray background, at least like 90% of it. And it's easy to assume that the rest of it is due to the sources that are too faint for us to detect. So the origin of the X-ray background seems to be reasonably well understood today. So even though that's only just few percent of starlight, right? The reason it's as much as 10%, a few percent of starlight, is that accretion to black holes is so much more efficient than thermonuclear reactions. Now, thermonuclear reactions convert much less than 1% of rest mass energy, rest mass into the energy. With black holes, you can do 10%. And so there are many fewer of these sources, but they're much more efficient in producing energy. And the gamma ray sources are believed to be almost all beamed active nuclei, blazars. We're looking down the jet. This is a picture of the gamma ray sky from Fermi satellite, added over 5 years. In a galactic plane, you have all manner of other stuff, supernova remnants and whatnot. At high latitudes, there are some pulsars, and mostly some of these beamed active nuclei looking at us. This is not 100% clear by now, but it's pretty close, and so this is a reasonable thing to assume. So you have these cosmic accelerators pointing at us, sending us high-energy photons, also probably high-energy cosmic rays. And so when you put it all together, this is what spectrum of the universe looks like. And each part has different contributions. In radio, it's mostly AGN from synchrotron emission. There is some star formation, H2 regions. Then in microwaves, it's cosmic nucleosynthesis in the early universe. And then from submillimeter to ultraviolet, it's mostly stars. And then accretion and black holes accounts for pretty much all the rest, and very high energies.